Right now, at this exact moment, the 27th of October, 2025, approximately 203 million kilometers from the Sun, an object from beyond our solar system is doing something that defies our understanding of natural comets. On the 21st of October 2025, at precisely 1442 UTC 3I, ATLAS passed directly behind the Sun from Earth's perspective, hidden from every telescope on our planet during what astronomers call solar conjunction. For 8 days, we've been blind to it. But here's what makes this moment unprecedented. Before it vanished, multiple observatories detected something that shouldn't exist in a natural object of its kind. The interstellar visitor designated 3I, Atlas, traveling at 245,000 kilometers per hour through our cosmic neighborhood, exhibits an anomalous mass that violates the statistical distribution of interstellar objects we should be detecting. Its minimum diameter is 5 kilometers, its mass exceeds 33 billion tons, and its trajectory aligns with the ecliptic plane with a probability of 1 in 500, three characteristics that individually might be curious. Together, they form a pattern that demands explanation. The NASA-funded Atlas Survey Telescope in Rio Hurtado, Chile, first captured 3I Atlas on the 1st of July 2025 at a distance of 670 million kilometers from the Sunday. Within hours, the Minor Planets Center received reports from 31 observatories worldwide, each confirming what the orbital calculations were already screaming: hyperbolic trajectory, interstellar origin, the third confirmed visitor from beyond our solar system. But 3I Atlas is not like its predecessors, where 1I, Oumuamua, measured perhaps 400 meters in length, and 2I, Borisov, showed a nucleus under 500 meters in diameter. 3I, Atlas dwarfs them by 3 to 5 orders of magnitude in mass. Think of it this way. If Oumuamua is a speedboat, 3I Atlas is an aircraft carrier. Given the limited reservoir of heavy elements ejected from exoplanetary systems into interstellar space, we should have detected approximately 100,000 smaller interstellar objects before encountering something of this scale. We've detected exactly 2. The Hubble Space Telescope photographed 3I Atlas on the 21st of July 2025, revealing a teardrop-shaped coma stretching 26,400 kilometers by 24,700 kilometers, nearly twice Earth's diameter. The James Webb Space Telescope pointed its near-infrared spectrograph at the object on the 6th of August 2025, measuring a mass loss rate of 150 kilograms per second at an outflow velocity of 440 meters per second. Normal comet behavior. But here's where the mathematics becomes disturbing. A team led by astrophysicist Richard Cloete analyzed 4,022 observations spanning several months, measuring the residual deviation in 3I Atlas's trajectory with unprecedented precision. The upper limit on positional residuals, 0.028 arcseconds. What this means is that any non-gravitational acceleration, any rocket effect from outgassing jets that typically nudge comets off their predicted paths, must be smaller than 15 meters per day squared. Given the measured mass loss rate from Webb data, this constraint yields a minimum mass of 33 billion tons. At solid density, that translates to a minimum diameter of 5 kilometers. The Hubble observation set an upper bound of 5.6 kilometers. We're looking at an object whose nucleus is almost certainly at the maximum size Hubble detected. Let that sink in. This is not a small, icy snowball. This is a mountain traveling through the void between stars that somehow maintains structural integrity over millions or billions of years of cosmic radiation, impacts, and thermal cycling. The statistical tension is profound. The interstellar mass budget, the total amount of rocky and icy material ejected from planetary systems across our galaxy, predicts a specific size distribution. Small objects should vastly outnumber large ones. We should be drowning in detections of 100-meter scale visitors before we ever glimpse a 5-kilometer giant. Yet, here we are. The Very Large Telescope in Chile obtained spectra of 3.1 Atlas in early August 2025, and the results introduced another anomaly into an already crowded field. The spectral signature showed nickel without corresponding iron absorption lines. Nickel. In industrial metallurgy, nickel alloys are prized for their strength, corrosion resistance, and high temperature stability. In natural solar system comets, nickel appears alongside iron in chondritic ratios. The primordial mixture from the protoplanetary disk. Pure nickel enrichment is not impossible in nature, but it requires specific formation environments, exotic parent body differentiation, or processes we don't typically associate with cometary nuclei. Then there's the trajectory. When you trace the orbital path of 3I, Atlas backward through the inner solar system, it approaches from the direction of Sagittarius, the galactic center, and its velocity vector at infinity is approximately 61 kilometers per second relative to the local standard of rest. But the critical detail is the inclination, 2.7 degrees to the ecliptic plane. Most comets from the Oort cloud arrive at random orientations, isotropically distributed across the celestial sphere. Interstellar objects should show even less preference, since they originate from star systems with arbitrary orientations relative to our own. The probability that a randomly oriented interstellar trajectory would align this closely with the plane containing Earth, Mars, Venus, and Jupiter is roughly 1 in 500. Coincidence? Perhaps. Or perhaps optimization. On the 29th of October 2025, just 2 days from now, 3I Atlas will reach perihelion, its closest approach to the Sun, at 1.4 astronomical units, roughly 210 million kilometers, just inside Mars's orbit. In orbital mechanics, this moment matters more than any other. The Oberth effect, named for German physicist Hermann Oberth, describes a fundamental principle. The most energy-efficient location for a spacecraft maneuver is at the point of maximum velocity, closest approach to a massive body. An impulse applied at perihelion, whether accelerating or decelerating, leverages the existing kinetic energy to maximize the change in trajectory for a given fuel expenditure. If you wanted to alter course efficiently, if you wanted to slow down or speed up or redirect toward a specific target in the inner solar system, you would fire your engines at perihelion. Here's the terrifying part. We cannot observe 3I Atlas during this window. Solar conjunction ended, but the geometry remains unfavorable. The comet is too close to the solar glare for ground-based telescopes. ESA's Jupiter Icy Moons Explorer, the JUICE spacecraft, will have line of sight during early November as it transits toward the Jovian system. But for the critical days surrounding October 29, we are functionally blind. If 3I Atlas executes a maneuver, if it deploys objects, if its trajectory deviates from gravitational prediction, we will not see it happen in real time. We will only detect the consequences when Earth-based observatories regain visibility in early December 2025. Let's construct 3 scenarios, not as definitive answers, but as frameworks for interpreting what we might observe when the viewing window reopens. Scenario 1. Natural comet, extreme member of the size distribution. In this interpretation, 3I, Atlas, represents the rare tail of a log normal mass function. Yes, we should have seen thousands of smaller objects first, but detection bias is real. Survey telescopes have only recently achieved the sensitivity to spot interstellar visitors. Atlas began full operation in 2015. The Vera Rubin Observatory just came online in 2025. Maybe smaller, faster objects transited before we were watching. Maybe 3. iAtlas is simply the first large one to pass during the brief window when humanity possessed the instruments to see it. The nickel signature could reflect an unusual parent body, perhaps a differentiated core from a destroyed exoplanet that wandered into interstellar space. The trajectory alignment might be selection bias. We notice the objects that pass through the populated ecliptic plane because that's where our planets and spacecraft reside. Under this model, we expect 3I, Atlas, to continue outbound from perihelion without deviation, possibly fragmenting due to thermal stress, like comet 332P, Ikea Murakami, which spun itself apart, or comet Shoemaker-Levy 9, torn by Jovian tides. If we observe a debris field, multiple fragments on slightly separated trajectories, that would support natural disintegration. The probability of this scenario, given current evidence, is difficult to quantify, but let's provisionally assign it 60% majority likelihood. Occam's razor. Scenario 2. Directed warning or signal. This interpretation posits that 3I, Atlas, is not passive debris but an intentional dispatch, a probe or beacon from an extrasolar civilization, designed to pass through our system along a trajectory calculated for maximum visibility. The ecliptic alignment ensures close approaches to multiple planets. 0.65 astronomical units from Venus on the 3rd of November 2025, 1.83 astronomical units from Earth on December 19, 2025, 0.31 astronomical units from Jupiter on the 16th of March 2026. A natural comet doesn't care where the planets are. A reconnaissance mission does. The timing of the solar conjunction perihelion maneuver would provide cover for course correction, shielded from observation, with results revealed only in December when we measure any deviation from purely gravitational motion. The large mass provides thermal inertia, shielding interior components from solar heating, and the outgassing coma provides natural camouflage, making the object appear conventionally cometary to casual inspection. Under this model, the Webb spectroscopy, the Hubble imagery, the size and composition data we've gathered so far represent external characteristics only, a skin layer 4 centimeters thick out of a 5-kilometer diameter, less than 0.00005 of the total mass. We cannot infer internal structure from a bladed surface material. If this scenario is correct, we might observe the following after perihelion. Trajectory deviation inconsistent with outgassing thrust, requiring a velocity change on the order of meters per second. Deployment of smaller objects, sub-kilometer scale, separating from the main body with distinct trajectories. Electromagnetic emissions, radio or optical signals, either continuous or pulsed. Alterations in rotation state. Brightness variations inconsistent with passive tumbling. The probability here is harder to assess. Prior probability of extraterrestrial probes in the solar system is conventionally assumed very low, but we've never had an interstellar visitor of this mass and trajectory alignment before. Let's assign 15% low but non-negligible given the accumulation of anomalies. Scenario 3, self-replicating seed or resource harvester. The most speculative interpretation invokes von Neumann probes, self-replicating machines hypothesized by mathematician John von Neumann in the 1940 seconds as a solution to the vast timescales of interstellar exploration. Under this model, 3I Atlas is not a single artifact, but a carrier vehicle designed to approach stellar systems, harvest resources, and dispatch daughter probes to continue the process. The large mass provides raw material for fabrication. The perihelion pass delivers 33 gigawatts of solar power to the surface, more energy than 1/3 of the 94 operating commercial nuclear reactors in the United States, sufficient to run industrial-scale manufacturing if captured and converted. The close approaches to multiple planets offer opportunities for gravitational assists, trajectory shaping without fuel expenditure, and potential material acquisition from planetary moons or atmospheres. If this scenario holds, we would expect the December observations to reveal a fleet of smaller objects, each potentially on different trajectories toward distinct targets within the solar system. The probability of this scenario is very low, perhaps 5%, but the implications are so profound that even a small percentage warrants serious observational follow-up. The remaining 20% probability I reserve for scenarios we haven't imagined, unknown natural processes, observational errors, or explanations that require physics beyond our current models. Now let's discuss the improbability stack, the cumulative list of characteristics that individually might be unremarkable, but collectively strain coincidence. First, mass. At 33 billion tons minimum, 3I, Atlas is 1,000 to 100,000 times more massive than the previous interstellar objects. Given a typical power law mass distribution with exponent negative 2.5, the ratio of objects in different size bins follows a steep curve. For every 5-kilometer object, we expect roughly 30,000 objects in the 500-meter range and 3 million in the 50-meter range. Detecting the giant first is like buying a lottery ticket and immediately winning the jackpot without ever purchasing a losing ticket. Possible, but eyebrow-raising. Probability of this mass being the first detection given standard distributions, approximately 0.0011 in 1,000. Second, trajectory inclination. The 2.7-degree alignment with the ecliptic plane places 3I Atlas in the bottom, 0.2% of possible inclinations, assuming isotropic arrival. Probability 0.002. Third, nickel detection without iron. While not impossible, differentiated bodies with pure nickel enrichment are rare even in our solar system. Most metallic meteorites show iron-nickel alloys in chondritic ratios. The VLT spectrum requires either an unusual formation history or industrial processing. Probability given natural origins, approximately 0.051 in 20. Fourth, activity at large heliocentric distance. TESS observations from May 7 through the 3rd of June 2025 showed 3I Atlas already active at 6.4 astronomical units from the Sun beyond Jupiter's orbit. Typical comets activate inside 3 astronomical units when water ice begins to sublimate. Early activities suggest supervolatile ices, carbon monoxide or carbon dioxide, which is consistent with an interstellar origin but adds to the unusual profile. Probability given standard comet composition, approximately 0.1. Fifth, lack of detectable non-gravitational acceleration. Despite vigorous outgassing, the trajectory shows no measurable deviation, implying extraordinary structural strength or internal mass concentration. Probability given observed outgassing rates, approximately 0.05. Sixth, green coma without expected molecular signatures. Early September 2025 observations detected a green glow typically associated with dicarbon fluorescence, but earlier Webb spectra didn't show sufficient dicarbon concentrations to explain the color. Something else is producing the emission. Probability of mismatched color versus composition, approximately 0.1. Seventh, anti-tail transition observed in September. Nordic optical telescope images captured the anti-tail initially pointing toward the sun in July and August, rotating to a conventional tail pointing away from the sun by September. This transition is consistent with changing solar illumination geometry, but the timing and symmetry are noteworthy. Probability of observing this specific transition, approximately 0.2. Multiply the independent probabilities. 0.001 times 0.002 times 0.05 times 0.1 times 0.05 times 0.1 times 0.2 equals 0.0000000001, 1 in 100 billion. Now, these probabilities are not truly independent. Many correlate with the object being large and interstellar, and my estimates are rough, subject to revision with better models. But even if we're off by several orders of magnitude, even if the true combined probability is 1 in a million instead of 1 in 100 billion, we're still looking at an exceptionally rare configuration. The Bayesian question becomes, which is more improbable? That 3I, Atlas, represents a 1 in a million coincidence of natural factors, or that it represents something deliberate? Before you answer, remember that absence of evidence is not evidence of absence. We've been capable of detecting interstellar visitors for less than a decade. Our sample size is 3. Drawing firm conclusions from 3 data points is premature. Science is not about jumping to sensational claims. Science is about following the evidence wherever it leads while acknowledging uncertainty. And right now, the evidence is telling us to watch very carefully. The institutional response has been measured, cautious, appropriate. NASA's Planetary Defense Coordination Office confirmed that 3I, Atlas poses no threat to Earth. Closest approach 1.83 astronomical units in December, roughly 274 million kilometers, no collision risk. This announcement came within 48 hours of the initial discovery confirmation, demonstrating the rapid coordination between survey telescopes and planetary defense networks. The International Astronomical Union's Minor Planet Center, the global clearinghouse for asteroid and comet observations, processed submissions from observatories spanning 6 continents, cross-referencing pre-discovery detections that extended back to the 7th of May 2025, when TESS had unknowingly captured the object during exoplanet transit observations. Multiple space assets have been tasked with observation. Hubble continues monitoring. Webb scheduled for another observation window in December post-perihelion. ESA's JUICE spacecraft during its November transit. Mars orbiters, including the Mars Reconnaissance Orbiter and ExoMars Trace Gas Orbiter, During the October 3 close approach to Mars, when 3.1 ATLAS passed just 30 million kilometers from the red planet. The Parker Solar Probe, designed to study the Sun's corona, adjusted its operational timeline to capture solar wind interactions with a coma during the perihelion pass, providing data on how the object's outgassing responds to intense solar radiation. Ground-based telescopes worldwide are coordinating observation campaigns for the December visibility window. The Gemini Observatory in Hawaii and Chile, the Very Large Telescope in the Atacama Desert, the Nordic Optical Telescope in the Canary Islands, and dozens of university-operated facilities have allocated time specifically for 3I Atlas follow-up. The Galileo Project, an initiative established specifically to search for evidence of extraterrestrial technology through systematic observation rather than speculation, has dedicated observatory time to monitoring for any deployed objects or anomalous activity. Their ground-based sensors, calibrated to detect small objects in Earth's atmosphere and near-Earth space, will track any material that might separate from the main body. There's been no suppression of data, no classified briefings beyond standard operational security, no conspiracy of silence. What there has been is an appropriate scientific caution. Extraordinary claims require extraordinary evidence, and while the anomalies are intriguing, they do not yet constitute proof of anything beyond a very unusual natural object. The delay in releasing certain data sets, Webb spectroscopy took weeks to process and calibrate. Hubble images required careful photometric analysis. These are normal timescales for space telescope observations. The instruments are in high demand. Multiple programs compete for observation time, and data reduction is computationally intensive. If anything, the rapid public release of preliminary findings, Loeb's blog posts, NASA's public updates suggest transparency rather than concealment. The scientific community is watching, debating, and following the data with rigor. So what should we be watching for when visibility resumes in early December 2025? First, trajectory deviation. Precise astrometry comparing predicted versus observed positions. If 3I Atlas emerges from solar conjunction on a path inconsistent with pure gravitational dynamics, if the residuals exceed the previous 0.028 arcsecond limit, that would indicate a velocity change occurred during the blind period. Even a small delta V, 10 meters per second, applied at perihelion via Oberth effect, would produce detectable deviations within days. Observatories equipped with high-precision astrometry, Gaia spacecraft, ground-based radar, if the geometry permits, will measure positions to sub-arcsecond accuracy. Second, morphological changes. Has the coma expanded, contracted, fragmented? Are there multiple discrete condensations indicating breakup or deployment? The Nordic Optical Telescope, Gemini Observatory, and other facilities will obtain deep imaging to resolve internal structure. Fragmentation would support natural comet behavior, thermal stress causing disintegration. A clean separation into distinct objects on diverging trajectories would suggest something else. Third, spectroscopic evolution. Do the emission lines change after perihelion? Does the nickel signature persist, strengthen, or vanish? Do new molecular species appear? Webb's infrared spectrograph can detect water, carbon monoxide, carbon dioxide, ammonia, methane, and complex organics. Any unexpected chemistry, silicon compounds, metallic vapors beyond what comets normally produce would be significant. Fourth, photometric variability. Brightness variations over time can reveal rotation state, surface features, or active regions. If 3I Atlas shows periodic brightness changes with a stable period, that indicates tumbling rotation. If the period changes, angular momentum is being exchanged, either through outgassing torques or internal mass redistribution. If the brightness is non-periodic, that's harder to explain naturally. Fifth, radio and electromagnetic emissions. The Very Large Array, the Atacama Large Millimeter Array, and other radio telescopes will scan for any emission beyond the expected thermal and molecular transitions. A narrow-band signal, amplitude modulation, or non-thermal spectrum would be a game-changer. Even a null detection is useful. It places upper limits on any potential transmission power. The 19th of December 2025 marks the closest approach to Earth, 1.83 astronomical units. Not close enough for detailed radar imaging from Arecibo, which is defunct, or Goldstone, which has limited sensitivity at that range, but close enough for excellent optical and infrared observations. This is our best window. The geometry places 3I, Atlas, against the background stars of Gemini, well positioned for northern hemisphere observers, high above the horizon for most of winter. Amateur astronomers with 8-inch telescopes might glimpse it as a faint smudge, magnitude 11 or 12, while professional observatories will resolve detail at sub-arcsecond resolution. Then, after Earth passage, 3I Atlas continues outbound, crossing Jupiter's orbit in March 2026 at 0.31 astronomical units from the gas giant, close enough that Jovian tidal forces could stress the nucleus if it's structurally weak. If it survives intact, that tells us something about internal cohesion. If it fragments, we'll have a debris field to study. Either outcome provides data. By mid-2026, 3I Atlas will be beyond Saturn, dimming rapidly, velocity carrying it back into interstellar space at 61 kilometers per second relative to the Sunday. Within a decade, it will be undetectable, lost against the background of distant stars, continuing its journey to wherever it was always going. We will have had one chance, one 9-month window from discovery in July 2025 to final observations in early 2026, to study the third interstellar visitor ever detected and by far the most anomalous. What we learn will depend on what we choose to look for. Let's return to the fundamental question, the one that haunts every astronomer staring at the data. Are we alone? For decades, SETI scanned the skies for radio signals, finding nothing but noise. The Fermi paradox asked, if intelligent life is common, where is everyone? The galaxy is 13 billion years old. Stellar systems have been forming and potentially hosting civilizations for most of that time. Even with conservative assumptions about the emergence of intelligence and technological capability, we should see evidence of expansion, megastructures, Dyson swarms, relativistic probes, silence. One resolution to the paradox: interstellar travel is harder than we think. The energy requirements too vast, the timescales too long. Civilizations stay home. Another resolution: civilizations self-destruct before achieving interstellar reach. Nuclear war, ecological collapse, AI misalignment. The great filter lies ahead of us. A third resolution: they're here but subtle, observing without interfering, sending probes disguised as natural objects, waiting to see if we notice. 3I. Atlas does not prove this third hypothesis, not even close. But it reminds us that our assumptions about what constitutes natural versus artificial are based on a sample size of one technological civilization, ours. We know what our probes look like. We don't know what an engineering tradition developed over millions of years, optimized for different physics, might produce. Could you engineer a probe to mimic a comet so well that only subtle statistical anomalies betray its nature? Almost certainly, if you cared to. Would you? That depends on your goals. If you're studying pre-technological or early technological species, if you're conducting a galactic census, if you're avoiding cultural contamination per some interstellar protocol, then camouflage makes sense. If you're announcing your presence, you send obvious signals, Arecibo messages, laser pulses, geometric structures. The fact that we haven't received an obvious hello might mean there's no one to send it, or it might mean the ones who are here prefer subtlety. We don't know. What we do know is this: the universe is not required to make sense to us. Reality doesn't care about our intuitions, our statistical comfort zones, or our philosophical preferences. It simply is. And our job as scientists, as conscious entities capable of measurement and reason, is to observe, to measure, to test hypotheses, and to update our models when the data demands it. 3i Atlas has given us data, lots of it, more than Oumuamua, which flashed through the inner system in weeks, more than 2i Borisov, which was clearly a comet and asked no difficult questions. We have spectra, we have imaging, we have mass estimates and trajectory calculations, and we will have more when December arrives. The correct response is not to declare alien technology based on incomplete evidence, nor is it to dismiss the anomalies because they make us uncomfortable. The correct response is to look harder, to deploy every instrument we have, to gather every possible data point, and to let the evidence speak. If 3i Atlas is a natural comet, wonderful. We've learned about the diversity of interstellar populations and the conditions in other stellar nurseries. If it's something else, well, that would be the most important discovery in human history. And we need to be sure before making that claim. Subscribe to this channel to stay on the timeline as this unfolds. December 2025 is not far away. The observation window opens, the data comes in, and we will analyze it together in real time. No hype, no sensationalism, just the physics and the evidence. When the James Webb images drop, when the astrometry shows whether the trajectory held or deviated, when the spectroscopy reveals what happened at perihelion, you'll see it here first, contextualized with the science, explained without dumbing down. Leave a comment. Do you think 3i Atlas is an extraordinary natural coincidence, or are we witnessing first contact conducted through orbital mechanics rather than radio waves? I want to hear your reasoning, not just your gut feeling. What would convince you one way or the other? What observation would shift your credence? This is not about belief. This is about evidence and inference under uncertainty. And right now, uncertainty is high, but it will decrease. That's the beauty of science. We don't have to speculate forever. We can measure, and measurement is truth. Here's why observation, even in the face of uncertainty, is our best instrument. Every great discovery in history began with something that didn't fit, an anomaly that refused to be ignored. Mercury's perihelion precession that led to general relativity, the ultraviolet catastrophe that birthed quantum mechanics, the cosmic microwave background that confirmed the Big Bang. Scientists didn't ignore the weird data because it was uncomfortable. They leaned into it. They tested it. They built new theories to accommodate it. Sometimes the anomaly turns out to be instrumental error or misinterpretation. And that's fine. You learn something about your equipment or your assumptions. Sometimes the anomaly opens a new door. We won't know which Category 3I Atlas falls into until we look. So we look, not because we expect aliens, not because we need cosmic companionship to feel less alone, but because that's what we do. We point our instruments at the unknown, and we take data. When the universe surprises us, when it hands us a 5-kilometer interstellar mountain, traveling at 245,000 kilometers per hour through the inner solar system, on a trajectory aligned with our planets and exhibiting a mass inconsistent with detection expectations, we don't shrug. We track it. We measure it. We extract every photon of information we can before it vanishes forever. And when the December observations come in, when the final astrometry is published, when the post-perihelion spectra are analyzed, we will know more than we know now. Maybe not everything, probably not everything, but more. And that incremental accumulation of knowledge, that patient building of understanding through observation and measurement, is the process that took us from cave dwellers wondering at the stars to a species capable of detecting visitors from other stars. It's the process that will carry us forward, whether we're alone in this galaxy or about to discover we never were. Keep watching the sky. Keep asking questions. And when 3I Atlas emerges from behind the sun in December, when the telescopes lock on and the data flows in, remember that you were here, paying attention, in the moment when we might have glimpsed something that changes everything, or confirmed that nature is stranger than we imagined, which is also a kind of revelation. Either way, we win, because in the end, the universe doesn't care what we believe. It only cares what we can measure. And measurement, precise and unforgiving, is the only truth we have.